All right, good morning, everybody, to our continuing discussion on graphing and increasing, decreasing behavior of functions. Before we get going, can I just get confirmation in the chat that you can see and hear me? All right, let's do this. Now, last time, let's think where we were. We are looking at increasing and decreasing behavior. And for that, we analyze the derivative of the function. And we ended with, oopsie, get out of there. We ended with y equals x to the 1/3, a simple version of a fraction power of x type function. And we saw that this graph has a vertical tangent line at y equals 0. So let's just make this a little bit more complicated. It's not as if these functions will always have a vertical tangent line, but often that's what we see and want to be prepared for when I see this type of function. So as I see these more and more, when I do my warm-up, I identify the function as a fraction power of x. I should think, ooh, watch out for vertical tangent lines. It's not a guarantee, but I should be aware that it is a possibility. And I'm building that experience slowly by looking at more and more examples. Let's make it a little bit more interesting, not super interesting, a little bit. And we will see these functions again. Let's look at this guy. X minus 1 all to the power of 2/3. Let me just make it clear what my denominator is. It is a 3. All right. So now I have no idea what this graph looks like. I see a fraction power. Yeah, the fact that it's x minus 1 in the bracket just means there's a little shift happening. It's not really a different type of function. So I am going to find the derivative. And that's going to be a chain rule. It's something to the power of 2/3. So the first part of the chain rule will be 2/3 times the something to the power 1 less, which will be negative 1/3, times, says the chain rule, by the derivative of that inside something, which is 1. Now, for the purposes of moving forward into my table and seeing what is happening with this derivative, I do want to clean this up as much as I can. For me, personal preference is to get rid of the negative exponent. So I will move it to the bottom. And perhaps I want to just remind myself that whenever I need to see it this way, this is just the cube root. Maybe that helps me, but either one of these I like before I move forward. So I have a reason to simplify because it's going to make my life easier for my upcoming table. So I'll do it over here. There are two things that I want to check. I want to check when is the derivative equal to 0 and when is the derivative undefined. Always going to be those two things, no more, no less. And the more we see them, the easier they will get. So I see that in my numerator, I only have 2/3. There are no x's, and only the numerator can make the function 0. So that's going to be a never. I do see I have something in my denominator. When x is equal to 1, I will get a 0, making the whole thing undefined. All right. So we will list all the numbers we get out of these two checks. In this case, there's only one. And I'm going to list all the pieces that I see. I see a 2/3, and I see a cube root of x minus 1. Together, they combine by way of multiplication and division to give me my derivative function. Now 2/3 is always positive, not a problem there, but I don't want to miss anything here. If that 2/3 was a negative 2/3, then it plays a bigger role. So I just get into the habit of listing absolutely everything I see in my function. Cube root of x minus 1 is 0 when x is 1, and because it's in the denominator, we've said it makes the derivative undefined. Okay. Now, this looks perhaps a little bit uncomfortable. To the left of 1 is this positive or negative. A shortcut that you can take to make it easier is I can take a representative number inside this interval. It's 0, so it's inside this interval. Plug in that number, but then I get cube root of negative 1, which is negative, and it's going to be negative for all of them, as long as I've listed everything that I got from these checks. And I've split up my table correctly. You can take a representative number, and whatever it does for that piece, the whole section will do the same. So I'll put a representative number of 2, something easy I can easily work with in my head. 2 minus 1 is 1, cube root of 1, positive. So that's one thing you can do if the component that you're looking at is a little bit less familiar. Now, a positive and a negative will always make a negative. 2 positives will always make a positive. So my slope lines are going down, bad things happening, going up. So it's not a little cup that it's making in the conventional sense, because I do not have, I'll emphasize it here, there's no horizontal tangent line here. That would be when the derivative is 0, and that's not the case here. So I do go from downhill to uphill, but let's see what's happening here. Let me set up a graph so I can at least visualize something. So, of course, we're just doing step 3. And again, that is not sufficient to clearly know what the graph looks like. If I did step 1 and 2, I would see that it goes up on either side. There is a y-intercept. Oopsie. What's my y? What's my y-intercept here? It's going to be 1, right? I don't know where these lines are coming from. Y-intercept of 1. Let's put it over there. And obviously something is happening at 1. Something unpleasant is happening at 1. The derivative is undefined. Yet, because I can see this as the cube root of x minus 1 squared, cube root is defined everywhere, this function is defined for all x values. So the function has no problem with any x values. It's the derivative that has a problem. And when I have a situation like that, for our level of functions, that's when I get the vertical tangent line, that there is a tangent line at 1. The only way the derivative cannot exist at the same time is if it's a vertical tangent line. Now I'm coming down and I'm going up. I'll give you a little, I guess, preview. You are not expected to know what this looks like at this stage because we don't have all the steps. We're just doing one step. I make a sharp point there. Vertical tangent line. Vertical tangent line. The more I see this, the better it'll get. I have a function value. It's defined there. The derivative is undefined. Has to be a vertical tangent line. Okay, but Looking at this function, if I did step 1, identifying it as the fraction power of x type, I know from the start to watch out for vertical tangent lines. And when I have all the steps, all the pieces will hint at that shape. So the more I do it, the better it's going to get. Slow and steady. All right. Again, feel free to interrupt me if you have any questions, like always. Okay, let's do an example with an exponential component. Those are probably my favorites because when I take the derivative, they're not going to be super difficult. I'm sticking to the natural exponential function. But at the same time, they give me more interesting examples than just polynomial or rational function, while not being too extreme with vertical tangent lines and difficult things like that. So I would do steps 1 and 2 maybe, or maybe a test question could just be find the intervals where it's increasing, decreasing. And I just realized we never wrote down our sentences here. I got a little excited about the graph. I'm sorry. We should write our sentences. Let's at least see the table here. Okay, so I can say here y, whoops, not eraser mode. You should always write your sentences. Y is increasing on 1 to infinity. Do I include 1 or not? Do I put a square bracket or a round bracket? I always want to make these intervals as big as possible. Even though the derivative is not defined, there is a point there. The graph is defined there. Include it. It's not about the derivative. It's about the function itself. And then y is decreasing on negative infinity to 1. Include it. If I compare any 2 points and 1 happens to be one of those 2 points, it's going down. It's part of that interval. So always write these sentences. I just forgot. Okay. All right. So before I move on to this example, actually, I want to classify these points that keep coming up that are interesting. When I look at this first example, I checked where is the derivative 0, where is the derivative undefined. We got an x equal to 1 coming out of that. And what I get here is a point where things are changing. It's going downhill to uphill. There's a turning point. It's an interesting point in the graph. We're going to call that a critical point. It's really critical to the property of the graph, to the features of the graph, to the type of graph that I see. Critical point is going to be 1, 0, the point 1, 0. Or I can say critical point at x equal to 1. Okay. Now, I don't have my other examples with me, but we saw other points coming out of this check, derivative equals 0, derivative undefined, and we'll call them critical points. So let me just classify that. A critical point, I won't be too fancy with this definition, is going to be when my function, my derivative is equal to 0 or my derivative is undefined. Undefined. All right, so those two situations could give me a critical point. And I always check those two. And, capital and, I have to have a point. It's critical It's important for my table out of these two checks. And it has to be a point, meaning my function is defined there. There has to be a point there. Now, if you think back to, let me just go quickly find that example that we did, the rational function one. We did this. You can look back on your notes. We did that yesterday. We found the derivative to be 2 over x plus 1. Everything's squared there. So when we then did our derivative equal to 0, we found never. Our derivative undefined. Yes, that was when x was equal to -1. This, however, is not a critical point because the function is not defined at x equal to -1. The original function has a problem there as well. It was a vertical asymptote, right? Quickly graph this. We had a vertical asymptote at -1. Horizontal one doesn't actually matter right now. We had a fundamental problem at -1. It jumps over. There is no point at x equal to -1. So it can't be classified as a critical point. It has to be critical, but it has to be a point for me to call it a critical point. Okay, so let's keep that in mind as we look at this function, and then we will see what the critical points are, if there are any. Okay, so I'm doing step 3. Step 3. Derivative is what I need to find. Clearly the product rule. Derivative of the first times the second plus the first times the derivative of the second. Now I want to clean this up. I want to know, moving forward, what is the best version I can get? Well, I'm going to take an e to the x out, and I'll have an x plus 1 or a 1 plus x left. That's the best I can make it look. I have a positive exponent there, so it stays above the line. Then I want to check, where is the derivative 0? Where is the derivative undefined? Always those two things, no more, no less. So now I have the luxury that I don't have a fraction to worry about. So it's going to be when either one of these two equals 0, right? It's going to be when either e to the x equals 0 or when x plus 1 equals 0. So I have from the second one, I certainly have a -1 for x. When is e to the x equal to 0 is my question to you. When is e to the x equal to 0? If I have a product, then I have to check each one of those factors, right? And whenever any one of them equals 0, that's an x value that I need to list. And I need to make sure I have all the x values. If I miss one, my table is going to be messed up. Everything is going to be messed up. I need to not miss one. So I get -1 from the second, x plus 1, obviously. But the other one, e to the x equal to 0, is also one that I need to check. But I know what my e to the x graph looks like, and I know it's always above the x-axis. It's never going to touch. There are none. So -1 is the only point. But you need to know. So never is the answer for e to the x equal to 0, and therefore I only have the -1. Picture the graph, read it off. It's all there. And undefined, all of these things are defined. I'm not dividing by 0. It's all good. So that's a never. So the only point of interest in terms of increasing, decreasing behavior is x equal to -1. I'll call this my potential critical point because I've done half of the check. I've done the top part. I need to make sure it's actually defined there. So we can check at this stage, or I'd like to do it after actually, but it doesn't really matter. I've cleaned up my derivative. I have a potential critical point. I'll check the function later when I write my sentences. I've sort of got into the habit of doing it everything at the end. I don't know why my line is so long, because only -1 is a point of interest here. So everything I list, e to the x, x plus 1, and they together give me the derivative. It has to be multiplication or division. I could not have taken the top, which had two terms. Okay, e to the x, again, I read it off my graph, it's always positive. X plus 1 is 0 when x is -1. It's in multiplication, going to make the derivative 0. X plus 1, check it, it's going to go negative to positive. So I have a positive and a negative, gives me a negative answer. Positive, positive gives me a positive answer. So my slope lines are going to go down, horizontal tangent, up. So a nice little cup shape that I get there. I don't know what my lines were doing there. Oh, there was one cup there. Whee! There we go. All right. Well, let's write our sentences. F is increasing on -1 to infinity. Do I include -1? Yes, I do, because I have a y value, plug it in, I can get a y value. Now I don't really care right now what the y value is. The important thing is that I get it. So y value exists. This function is defined for all x, because why not? E to the x is defined everywhere. X, no, no division by anything. There's no problem at all. I can maybe write without. I just don't want a decimal number here. It's gonna be negative e to the -1, right? Whatever -1 over e is. Who cares? It exists. That's the only thing that's important. And f is decreasing on -infinity to -1. Critical point? Yes. It's at x equal to -1 because it came out of my check of the derivative and there's an actual y value. There is a point. Critical point. But of course, I have no idea what the graph looks like. Who knows? And I'm going to leave this a mystery because I don't want us to think that we're expected to know. I have no idea what this graph looks like. I need all the pieces of the puzzle. Personally, I still need all the pieces of the puzzle. Unless I've seen the exact one before, the fact that I've seen maybe x times e to the -x is a completely different function. I can't guess even what this looks like. Does it have asymptotes? I have to do step 2. I don't know, but that's not the point right now. So in the midterm as well, in a test, you might be asked to just do a single step and you won't know what the graph is and you're not going to be expected to graph it either. Just make sure that you can write these sentences at the end. Very important. If you don't write the sentence, I cannot give you all the marks. I need to see that interval. I need to see what you're including and everything. Okay. Any questions so far? I think that's good enough for now for our examples on increasing and decreasing behavior. We have the rest of today and tomorrow to get through step 4 And then next week after the midterm, we will focus on putting all the information, all the pieces of the puzzle together. So we have one more step. Why do we have one more step? Now, for some simple functions, steps 2 and 3, asymptotic behavior, long-term behavior, increasing, decreasing behavior, will be sufficient to have a pretty good guess of what the graph looks like. But if I want to perfectly know what the graph looks like, every little bit of it, there's something missing. If I just stop at increasing, decreasing behavior, notice that I can have many functions or many graphs that are, for example, increasing. A function can be increasing in many ways. Let's visualize that. It can be increasing like this. That's definitely uphill. But it can also be increasing like this. They're both increasing. Any tangent line has a positive slope. And just saying, oh, it's increasing there, that doesn't quite tell me the shape of that graph. Something is missing. I have a similar issue with decreasing. A function can be decreasing in many ways. My writing is not very good today. I apologize. Is it ever good? No. If I look at decreasing, I have a similar issue. I can go downhill and sort of slow down, right? The tangent lines are getting flatter. Or I can go downhill slowly and then speed up. They're both downhill. They're both decreasing, but they are not the same. It's not the same shape. And to be accurate in my graph and my analysis, I kind of want to know, well, which one is happening here? All right. So let's notice the difference and similarities here between these four graphs. Think of a thin rod and you're bending it. In order for me to get a shape like this, my hands are at the ends of this rod. I have to bend it up. My hands have to move up and make sort of a half smile. Same for this one at the bottom left. My hands have to move the same way to create this bend. It's just tilted a different way. So we're going to call this we're going to say here the graph is concave up. And this one as well. The bend is the same. So I'm focusing on how the graph bends, not how it sits increasing, decreasing, because I've done that already. I'm looking for another kind of property, the bend in the graph. And if I look at the right two, my hands have to move down to create this bend. It might not be a full bend, but it has to bend down. I'll call this concave down. This one as well, concave down. Now in some cases, I might get a full bend, right? I have a longer rod, I bend it completely, hopefully it's not too hard to bend, and I get a full turn, nice smiley face. So I do think of this situation because it's easier to remember. When I'm up, I am happy. When I'm happy, I smile. Concave up. When I'm sad, I am down. When I'm down, I frown. concave, down. So it's pretty easy to remember which is which. But know that it doesn't have to be a full turn. It could be a little half smile or a little half frown. Concave up, concave down. Okay. Now, how am I going to figure out which aspect of the function leads to the way it bends? So let's make a new page. First of all, I just want to call this step 4. The bend in the graph, we call that the concavity. Concavity. How it bends. Now, let's take a side note. Let me just take a side note. Take a function. I don't care what function. Let's call it g. Take a function g of x. Remember that this function is increasing, forgetting the 0 part of it, whenever the derivative is positive. I later on include the 0. I don't want to worry about a technicality. Let's just think positive. Okay. Regardless of the function, if it's increasing, its derivative is positive. If its derivative is positive, it's increasing. Okay. So let's keep that in mind. Now let's just look at the classic concave up. Big smile. Actually, I'm going to write it at the bottom. Big smile. Best case scenario. And let's call this guy f of x. So if f of x is looking like this, concave up, what can I say about the slope values? Well, let's take some points of interest here. Let's take this point, and this point, and this point, and this point, and this point. Of course, there are many. I'm just taking some of them. And let's look at some tangent lines here. This tangent line over here, maybe its slope, it's pretty negative, right? It's pretty steep. Let's say it's -10. This slope over here, ooh, that was supposed to be a straight line. It's a little flatter, but it's still negative. Maybe it's a -2. This guy at the bottom, that's going to be horizontal, slope 0. This guy over here, well, he's a little flat, but he's positive. Let's say it's slope 2. Just examples, right? The one on the right here, it's a little steeper, but positive. Let's say its slope is 10. Just examples. So, in this situation, I have slope values among many others. They go -10, -2, 0, 2, 10, and of course they keep going, and there's stuff in between and whatever. This sequence of numbers is an increasing sequence. Increasing, right? They're getting bigger. Increasing slope values. So if I look at the function that gives me these slope values, the function is going to give me a -10 and a -2 as I move from left to right. It's going to be an increasing function. Let me say slope function. Let me say slope function. The function that gives me these slope values will be increasing. And what function gives me slope values? That was a question to you. What is the function that corresponds to the slopes of tangent lines? I give you all the easy questions. No one. All right. recognize. It is, of course, the derivative. So the derivative of the function is of f is an increasing function. Is my mic still working? I sometimes wonder. So now, what does that mean? Remember up here our side note that if I have a function, I don't care where it comes from. If it's increasing, its derivative is zero. Greater than zero, sorry. Let's write the derivative like this. Now I have a function. Stop that stupid lines. I have a function right here. That's a function. I don't care where it comes from. Its derivative has to be positive. So what I have here is the derivative of the derivative of f of my function. We're going to call that the second derivative, the derivative of the derivative. So I have multiple layers of derivatives because when I take the derivative, I get a function. Who says I can't take the derivative of that function? And in fact, that second derivative is going to tell me how the graph bends. Now for short, we're just going to write this as f double prime. And that is going to be what we have to look at. Now I can do a very similar thing for concave down. If I'm concave down, my slope values will be decreasing, and my second derivative has to be negative. All right, let's get some examples going. Again, we're going to continue with more examples tomorrow, and that'll be the end of our discussion focusing on one step at a time. Just because I'm paranoid, can someone just confirm in the chat that my mic is actually working? Because no one responded to my question. I wonder if it is actually still working. Maybe I've been talking to myself for 20 minutes and no one says anything. Okay, good. So, example time. Now again, it's more than anything else really. If I just do step 4 and find where the graph bends, I have no idea what the graph looks like. I have no idea. I need it as the final piece to my puzzle, but the only piece, I can't see the puzzle. So let's look at a function. X to the 4 minus 8x cubed plus 18x squared. There's a function. I don't know what it looks like. Who knows? Now, in order for me to do step 4, I need to find the second derivative. In order for me to find the second derivative, I need to first get the derivative, also called the first derivative. So step 4 is usually done after step 3 because in step 3 I would need to find the derivative and then step 4 builds on that derivative. So I can't really skip that. I have to find the derivative first. 4x cubed minus 24x squared plus 36x. That's just the first derivative. Now this is going to be a pretty okay version for me to find the second derivative, which is now the derivative of this function, right? Derivative of this function. So it is just the basic properties, 12x squared minus 48x plus 36. Now, I'm going to do the table on this second derivative function. So there's going to be a lot of similarities between step 3 and step 4, except the function that I'm using my table for is different. It's going to be this guy, which means I need to clean him up. I can only do the table for multiplication or division, not addition and subtraction. Well, at the very least, let's take out a 12 and give myself a fighting chance for this factoring. That means I have x squared left, and I have a minus 4x and a plus 3. Okay, that looks way better. So hopefully we can factor that. I'll have an x and an x. I'll have a minus 3 and a minus 1. Whew, that wasn't so bad. I'm going to do almost everything exactly the same. It's just going to apply to the second derivative. I'm going to again check where is this second derivative equal to 0 and where is the second derivative undefined. Now I know for this it's a polynomial, it's never going to be undefined, but there are going to be some functions where I need to check both, right? Where is the second derivative 0? Clearly when x is 1 and 3. Okay. So we're making progress. Now everything that I get out of this check, those are the x values that I'm going to list, and that's going to split my x-axis up into, in this case, 3 intervals. Now I list all the pieces that I see in my second derivative. By way of multiplication, they combine to give me the second derivative. 12 is always positive, but I don't want to leave it out. It's a part of it. Let's include it. X minus 3 is 0 when x is 3. In multiplication, it makes the second derivative 0. It's going to go negative to positive. Because it's a familiar x plus or minus a number, I get used to those very quickly. Anything else, I need to make sure. I need to always be sure. But repetition definitely makes these guys easier. X minus 1 is 0 when x is 1. It's just being multiplied, so it's making the second derivative 0. It's going to also go negative to positive. But do make sure for yourself that you're happy with that. I have a positive and 2 negatives. Answer will be positive. I have 1 negative here. Answer will be negative. No negatives. Answer will be positive. So now, this is the second derivative. No slope lines. That's not what we're doing here. So what I like to do is just have the little smiley face or the little sad face, little smiley face, to help me remember what does the plus mean here? Oh, it's bending up. It does not mean it's a full bend, up or down. Sometimes not. I don't know. It's just going to bend that way. It could be just that little section of a bend. It's still the same kind of bend, concave up. Okay, so this is just a reminder for me what is happening. Let's write our sentences. Now, of course, we are still trying to make statements about the original function. F is concave up on negative infinity to 1, as well as 3 to infinity. Same rules for including the endpoints because I have a polynomial. It's defined for all x values, which means I have y values here. I'm not going to bother calculating them. Plug it into your calculator, you get an answer. Do I have an answer? I actually do. Wow, look at me. I just didn't want to waste time to calculate it now. When x is equal to 1, I get an 11. Correct me if I'm wrong here. And a 27 when x is equal to 3. So I get y values. I can include them. There are points, regardless of what the second derivative does. So again, just want to clarify because I don't know what you're thinking. I'm totally guessing. Zeros here do not mean horizontal tangents or anything. It's the second derivative. Second derivative. even though my table method is sort of recycled. It's a different function, different conclusions that I'm making. F is concave down on 1, 2, 3. 1, comma 3. All right. So now when I look at the critical points, in step 3, I looked at the derivative. I was searching for where it's increasing and decreasing the function. I got these interesting points out of the check for the first derivative. And if they were actual points, I call them critical points. I'm going to do the same thing here because I'm pretty much doing the same thing. I have these similar two checks. Points come out of it, but I can't call them critical points, right? It's a different situation. I need to call them something else because they're also important, but I can't use the same word. Now, before I do that, I think maybe seeing this graph might help me. Even though just from this, you are not expected to know, and I won't know. I need all the pieces. I don't know what this graph looks like. I am cheating and giving you the answer. It is not obvious from the information that we have. So please be aware of that. So I actually have a horizontal tangent here at 0. And I'm going to come through that. Of course, all that information comes from step 3. At 1, I have what I said, 11. And the bend, see the bend in the graph is up. It actually goes through a full turn. Then over here, remember at the top there, you see it bends up. At 1, it changes to bending down. Whoops, that's wobbly, I'm sorry. I don't remember if it's if it's horizontal here. I actually don't remember. Because I didn't do that step, I don't know. I can't remember. It bends down just a little bit, not a full turn, to where x is 3. And then it bends up again. Whee! Off to infinity. So I have up bend, down bend, up bend. So I have these important points that came from the check and the fact that there are points. We're going to call them inflection points. So it's very similar to, was it this page? Yes, to critical points. Except it's going to come out when the second derivative is 0 or the second derivative is undefined. So that's still my check, but now applied to the second derivative. And I have to have a point. So my function is defined there. There is a y value. There is a point. See, it's just like this one. But, of course, it can't be perfectly the same. There's another and. And the concavity or the bend in the graph must change as I cross that x value. I read that off my table. See how it changes from a plus to a minus, inflection point. Minus to a plus, inflection point. So in this case, both of these guys are inflection points because they satisfy the 3 conditions. X equal to 1, x equal to 3. They come out of my check, or my second derivative. There are points. The bend changes as well. Now, I challenge you, if you have nothing else to do, can you come up with a polynomial function where I get points out of the check? They're points, they're defined, they're y values, yet the bend doesn't change, and they're not technically inflection points. It's either a plus to a plus or a minus to a minus. If you want, think about it. Otherwise, tomorrow, first thing, we will look at an example like that, just to show that not all of the points that come out of this are necessarily classified as inflection points. They're potentially inflection points until I check all the way at the end did the bend actually change. But like always, we're pausing. We have all of tomorrow still to just do examples. Bring your questions. Make sure you understand. A lot of information is happening. Make sure you are on top of things. Are there any questions at this stage before we pause and pick it up tomorrow? All right, then I will leave it until next time. See you tomorrow.